So here we'll start our session, today's session. So generally, current what and all the topic I have selected. So that will go with the flow of, and I'll start with the intro of the nanomaterials. Then we'll go for the types of nanomaterials. Then we have compared the traditional versus the green synthesis. So green synthesis means everybody knows that with the plant materials we are using that. So why we are using the plant materials and how to select the plant materials. After selecting the plant materials, how the synthesis will take place. And after the synthesis, how the characterization will take place. Then after the characterization, so then we'll move on to the case studies, which I have done in my PhD. So that only I am going to present now. So now coming to the first one, as we know that nanomaterials are the particles which are lies within a dimensions between 1 to 10 micrometers. Nanomaterials is derived from a Greek word which means dwarf. That means in the nanomaterials only, nano, in the Greek word we will call it as an nanos, which means a dwarf are extremely small. So due to their small size, so they oftenly exhibit unique properties such as physical properties, chemical properties, chemical, biological properties, all will be compared with the bulk components. Now in that unique properties will go on to the size dependent properties. So this is the main thing we have to focus in this. So size dependent properties, if you take means, so in this we will check with due to their small size, how the physical structure will be there, then chemical structure will be there, then after that biological properties are there. So when we are significantly, we'll compare it to the bulk materials. Is it audible, ma'am? My voice is audible, or shall I need to increase more, ma'am?
Oh, ma'am, audible.
Yes, ma'am. So then we'll move on to the next one, types of nanomaterials. So types of nanomaterials, we know that there are different types of nanomaterials. Particularly here, we're focusing on the 0-dimensional, 1-dimensional, 2-dimensional, and 3D dimensional. So in that only I have specified that nanoparticles, nanotubes, nanowires, nanosheets. So nanoparticles which comes under the dimensions is less than 100 nanometers. So for example, if you take so here we are having a gold nanoparticles, silver nanoparticles are there. So with this gold nanoparticles and silver nanoparticles, we are doing the research on the cancer treatments. So they will directly target the cancer cells and all. So next one, nanotubes. So nanotubes will comes under the 1-dimensional nanomaterial type. So these are cylindrical nanostructures. So with their remarkable mechanical, electrical, and thermal properties are there, such as carbon nanotubes, carbon nanowires are there, rods are there. All these are the examples for this nanotubes, which comes under the 1 dimension. So then 2D dimensions, if you take means nanowires will be there. So these wire-like structures, which is having a diameter range only will be there. So carbon coated, here you can see in the images where we have mentioned clearly that thin films, plates, layered structures are there in the 2D type. Whereas in 3D type, you can find the bulk nanomaterials, which is having an polycrystals. For example, liposomes will be there. Next, dendrites will be there. All these will come under the 3D dimensional. So this is the thing. Next, we'll move on to the next one. So that is an traditional versus green synthesis. So traditional versus green synthesis means, so traditionally what we are practicing, that means based upon the physical and chemical, how we are doing that one. So which refers to an conventional method. So traditional synthesis is nothing but so conventional method where we are used to create the nanomaterials. So in this, we have some drawbacks is there. So that means, so while using this traditional synthesis, so there are, we can generate the toxic byproducts will be generated in this. So even though we can create the nanomaterials, but it will generate the hazardous materials because it involves the chemical reactions. And there are some common techniques where we are using in this traditional synthesis is chemical vapor deposition method is there, and physical vapor deposition and high energy ball milling method. And here there are the risk factors also more are there in the traditional chemistry, traditional synthesis and all. So then in that, the utilization of stoichiometric reagents are also is there. And when coming to the green synthesis, so overall by overcoming these things and all, now we are moving towards the next one, that is an green synthesis, so which is an eco-friendly and sustainable also. Here we can do the biodegradability also, we can do that, and this method is an biocompatible also. And here we will use only the natural one, natural plant-based materials. So where we are getting from the nature, and the non-toxic materials will be very less when compared to the traditional synthesis and all. And the wastage also will be minimized, and energy consumption also will take less time when compared to the traditional synthesis and all. And here we are using the, either we can use the plant extract or we can use the microorganisms for the synthesis of this nano materials. Now we choose the next one. Next one. So here in this we are having a next one, we are having a flow chart based on this. We can clearly we can say that, so by which method if you are doing this, what kind of things we can be done. So generally synthesis of nanomaterials can be done in two methods. If you are using a traditional method, so here we'll go with the one is on chemical method will be there, and another one is on physical method. And we can take the nanoparticles like silver, gold, copper, titanium oxide, zinc oxide, all this also we can take for the synthesis of the nanoparticles. And if you come to the green synthesis, this is a newly bio-inspired strategy. Either we can take the plant material, any part of the plant we can take. Either we can take the leaves, roots, flowers, fruits. So in all these things we can extract, we can synthesize the nanomaterials. Then microorganisms, if you are taking, means in this also bacteria, fungi, from algae, all these also we can synthesize the nanomaterials. And later on synthesizing it, then we'll go with the characterization. Then we can apply for the application side, drug delivery system. We can use this nanomaterials. Then agricultural side we can use the nanomaterials. And X-ray imaging also we can take it. Then after that, even in the food packing also, and aircraft components, all these things and all we can use after the synthesizing of nanomaterials from the plant-based materials. Now, the next question is why we are using this plant materials. So why we are using this plant materials means the main reasons are there. So because when you are going with the traditional thing, so there we are having an high toxic materials, byproducts will be eliminated, will be formed as an byproducts during the synthesizing of nanomaterials. So because we are using an high conventional methods and all, so that's why there are some drawbacks in that when compared to the plant-based materials. So here we are taking the plants which are obtained from nature, and we have several advantages that to in an attractive option. So first one, here we are go with the environmental and healthy benefits. So it is an eco-friendly is there, and which reduces the toxicity, and it is safe while doing the synthesis process also. The people who are those who are working on this, so they'll feel the safety will be there. So it will not more hazardous, it will not cause any cancer or any health related diseases will not occur. So that is the first thing. And the second thing is an cost effectiveness. So because these are available in and around us, so that's why the cost will be low, cost will be there, and the resource efficiency also we can take. And the next one is an versatility and richness of the natural compounds. Because so all the components, whatever the plant materials you are taking, so it may act as an natural stabilizers or phytochemicals also. So with this phytochemicals is nothing but where we can find the active components. When you are taking a traditional synthesis, so by taking an artificial materials and all, so there we may find some materials will be having an high active, some materials will have an low activeness will be there, but almost all in all the plant materials we can have an all the phytochemical, that means active components will be there. And the next one is an biocompatibility and functionalization. So this is also one of the advantage. Here you are taking a natural plant materials, so it is an biocompatible also. So once the process is done, you can whatever the waste products we are getting, so that and all also biocompatibility we can do that. And here there are few examples I have taken. So one is an gold nanoparticles, so which is obtained from a neem tree. So that is where generally we will call it as an Ajaradata indica. And silver nanoparticles we will get it from an garlic as well as tea, and coriander also we can get the silver nanoparticles. Then the next slide we'll move on to the next one. So plant material selection. So this is a very, very important step while we are doing the synthesis or synthesis of nanomaterials on the plant material. So here we are having, and I told you that phytochemical composition we have to check. So according to that only we are going to do that. So first of all, phytochemical composition we have to check. Before that, type of the plant material. So what type of plant material you are choosing? So that is also very, very important. So if you are taking a plant material, either it is an leaf or root or maybe a fruit or seed, flower or bark and wood, any type of any part of the plant material. So each part of the plant material will have an specific and unique properties also. If you are taking the leaves, so these are rich in antioxidants, and where we can synthesize the metal nanoparticles. So if you are using a leaf from a plant material, any plant material, so there it is rich in antioxidants, and we can synthesize the metal nanoparticles. Suppose if you are taking a root, so there the bioactive components, we will find out the saponins, alkaloids will be there, where it will act as an reducing agents as well as the stabilizing agents also. So what is the stabilizing agents and reducing agents means? So in a reducing agents, where you can find the flavonoids, phenolics, alkaloids, terpenoids, natural products and all will be obtained in that reducing agents and all. Whereas stabilizing agents means, so these will act as an capping agents. So where we can prevent the agglomeration and all, we can prevent during the synthesis of nanoparticles. If you are taking the root part, in that you are having the saponins will be there, then alkaloids will be there, so which acts as and which is useful for reducing and stabilizing the nanoparticles. Then if you are using a fruit and seed, so these are rich in sugars and acids also. So this fruit and seed also we can use it as an both ways, as well as both reducing agent as well as the capping agent. And flower, if you are taking means, there you can find the pigments like anthocyanins and flavonoids will be there, which are effective during the natural nanoparticle synthesis. And bark and wood, if you are taking means, so they are having a high concentration of tannins and polyphenols will be there, so which will be useful for reducing metal ions. Then we'll move on to the next slide. And here also there are other criteria are also there, availability and sustainability. So we told that plant materials we can take within in and around. So even though in that case also we have to check the availability and sustainability. So availability means local availability. First of all, we have to give the preference to our local available. So whether it is an abundant or not, where we can reduce the cost and environmental impact, all these should be considered in a local availability. And sustainable harvesting also. So ensuring the plant material can be harvested without causing any ecological damages or depleting resources. So if you are consuming the plant materials without any backup or without any, if any causes any ecological damage, that is also one of the point we have to consider. So whatever you are using, that should be harvestable. So that only, so we can protect our environment. Next one, specific applications. Then here also we have to check. So different plant materials we are taking. So even though you are choosing based on the desired properties of your nanomaterials. So here we will take the size, shape, functionality. All these should be present in that plant materials. So that means specific phytochemical plants only we have to select. And the next one is an environmental impact. Here we are checking the two things. One is an biodegradability. So here the byproducts and waste products, whatever we are getting, there should be an biodegradable, and it should have a minimal environmental impact. It should not affect the environment more. So some or other how we have an environmental impact will be there. So in such cases, whatever the plant materials you are using, that should be an biodegradable, that waste and byproducts, whatever we are getting after the synthesis, it should have a minimal environment effect should be there. And the low energy requirement. So during this extraction synthesis process, we will require very low energy inputs only. No need to put a more energy inputs and all. So while contributing to the overall sustainability, this method is by taking the plant material, we can synthesize the nanomaterials. And we have to go check through the case studies and precedents also. So here documentation also we have to be check. That means if you are selecting any plant, why I have mentioned this case studies during the plant material selection means because we have to know the if we are taking any plant material to synthesize. So before the things we have to search, that means literature survey should be in a proper way. That means we should know that. So if you are taking that particular plant, how much success they have done. So what is the research progress in that? All the previous studies should be known to synthesize the nanomaterials, where we can provide an efficiency and potentials, limitations, what and all the limitations they have set, that we can cross it by seeing the documentation. Then we'll move on to the next slide. So where we can see the extraction. So this is the now the next step after selecting the plant materials. Now we have selected now we are going with the synthesis of nanomaterials. So if you see the picture, we can clearly note it down. We can clearly say that so this is a plant material, any part of the plant we are taking. So then we'll go for the extraction of the bioactive components. So then after that, after extracting, you may get the essential oils you can get or any extract of the plant materials that we can get it. So after that, we'll go with the nanomaterial biosynthesis. So in this nanomaterial biosynthesis, we can get the nanoparticles. So that only we have mentioned. So here different plant parts we can take, we can be used for the preparing the extracts of oils that and all by using and various techniques such as macration and extraction by using a rotary evaporator. Here is the rotary evaporator is there. So with that, we are going to extract the plant material. After extracting, we will synthesize the nanomaterials through different protocols that may or may not involve the heating. And we have mentioned the reference also below that from where we have got this information and all that I have included the reference. So next we'll move on to the next slide. So next slide. So here this is an after synthesizing, here we have to follow the things like isolation and preparation of an plant extract. So generally we'll take the plant extracts, we will follow the following steps. So initially collection of plant materials we will take. So selection and collection of plant materials. So from that we will prepare the preparation of plant material we will prepare. Then after that filtration we will do. Then after that isolation, purification, drying. All these things will be done during the synthesis of the nanomaterials. So in the selection and collection of the plant materials, here we will choose the plant materials, any part of the plant materials you can take it. So from that we will extract the compounds. So after that, so initially collection means where we will go where we will search that what kind of plant you want, so that you will collect the plant materials which are highest concentration. So where you can extract the active components. So for the preparation of your plant materials, in a raw material we will take that. So in this raw material here, first of all we have to clean it, then dry it. In drying also two methods we will use. One is an air drying and oven drying is there. After that only we'll go for the grinding purpose. So cleaning, everybody knows that the remove of the foreign particles and all. Next drying means we will dry the type of extract. Then air drying, oven drying will be there. So why we are doing this means that during the presence of sunlight, and oven drying is at the low temperatures, we will do that. Any bacteria or any other things are there. So unwanted material that will be removed from this. Then we will go with the grinding method where we will get an porous material. Coarse or fine powdered form will be obtained by this grinding. So next one we'll go with the other criteria also, other process also which are involved in. So now this is an extraction method. After grinding, we'll go with the extraction method. Here we will do the solvent extraction. So after extracting, you may get it in the form of an powdered form, or you can get it in an oil form also. So that we are doing this solvent extraction form. So use the solvents to dissolve the desired compound. So one is an macration. So macration is nothing but we will soak the plant material with the solvent. So we will check the suitability of the solvent, whether your plant material will be soluble with ethanol or any other solvents like ethanol, methanol or water for a particular period. Then we will shake occasionally, we will change the things. Then we'll go with the percolation method where the continuous passage of the solvent will be there throughout the plant material until you get the desired compounds of it. Then the next one is an oxalate extraction. So this is a repeated process where you are getting your extract with the solvent. Next, distillation, cold pressing, and supercritical fluid extraction. All these are involved to extract the essential oils from your plant material. Then we'll go to the next one. So that is next slide. So that is on filtration and concentration. So here, after this extraction, now we are filtrating the residues, whatever the solid residue you are getting, that we can do it with either you can use the filter paper process or centrifugation process or membrane filter process. So any of the one of the method we can use it to filter the extract and to remove the solid residue in that. Then concentration also we will check it. So during this, any evaporation will happen after your extract is concentrated. So then any evaporation will happen under the residues pressure or by freeze drying method. All these conditions we will check. Now after the filtration concentration, now we'll go for the whatever the extract we got. So with that we will check the characterization. So in this characterization, generally we will do the two steps. One is a preliminary test where we can test your extract of its phytochemical content, whether that having an either phenolic is there or flavonoids is there, any other natural products are there in that we will check phytochemical content, we will check, and biological activity also we will note it down in the preliminary test. So based on this flavonoids, phenolics, or whatever the phytochemical contents are present in that extract, so with that we can say that what kind of biological activity is there, whether it is related to the anti-cancer or antimicrobial or anti-inflammatory, that we can check by this preliminary test. So after this preliminary test, we'll go with the characterization techniques. So where you can know that UV visible spectroscopy is there, and HPLC method and mass spectroscopy to analyze the extract composition. Then after your extraction, now the main step came, that is some synthesis of nanomaterials. So now in the synthesis of nanomaterials, whatever the plant materials, whether it may be an reducing agents or it may be an stabilizing agents or whatever the things, so that we will done via chemical reduction or green synthesis or biological methods and all. So green synthesis is nothing but, so where I told you that plant extract with the metal salt and the other precursors we will take. So where it will reduce us to the metal ions, from that metal ions to we will get the nanoparticles. Then if you are opting a chemical reduction process, so it is a combination of chemical reagents where it will reduce us the metal salts. From that metal salts we can get the nanoparticles. So next slide, it can clearly state you that the flow chart will represent how the synthesis will happen. So here you can see that bioreductant from either you can take it from the microorganisms, that means bacteria or fungi or any plant material, along with that metal ions. So both the ways we have mentioned here, maybe it may be an enzyme or phytochemical things. So initially metal nanoparticles in the solution will happen based upon all these criteria, that means reductant concentration, their pH, kinetics, mixing ratio, incubation time, all these things, we will get the metal nanoparticles in the solution. So after that, we'll do the characterization. So by using any one of the methods. So here we have using the UV visible analysis and nanoparticle powder we will get. Then we'll go with the SEM, TEM, DLS, XRD things. So where physiochemical characterization will be there. So if it doesn't meet the size and shape, so the distribution criteria is not there, means we will modify the process. If it meeting the criteria of size, shape, then this distribution criteria, it is meeting unique properties criteria is meeting, means, so then we'll go for the biofunctionalization. Then we will use for the whatever the purpose we are using, like that we can check it. So this is the general process where we can, general protocol where we will follow for the synthesis. Then in a characterization, so in a characterization, generally we'll go with the size and shape analysis. So for this size and shape analysis, we are having an unique special techniques are there. That is an TEM we are using, and SEM also we are using, DLS, dynamic light scattering. So where we can analyze the size and shape of your nanoparticles. Then structural analysis also is there. So where we can employ the X-ray diffraction, Fourier FTIR also to study the structural properties. So with this, we'll confirm the composition of the nanomaterials. Then after that, we'll go with the stability and application testings. So stability, access the stability for the synthesized under the various conditions. You will check the stability of your plant materials, how the stability conditions are there. Then after the stability, we'll go with the application testings, so that it may suits with the intended applications, like whether you are opting for the medical field or you are opting for the agriculture or you are opting for the electronics. So whatever the application purpose you are using, so that we can evaluate, and with the performance we can say that whether it is an effective or not. So this nanomaterial we can use it or not, we will confirm in the application testing and all. Then we'll go with the next one. So here is the applications of nanomaterials. So after that, in this application testings only, so these are the various things. So we can use it for the nanomaterials, we can use it for the catalysis, biomedical, electronics, food industries, food safety, aerospace and defense, and these are the main applications we are using. So once you have finalized your plant material, you can opt any one of this. So with this, we can continue our research. So in case catalytic, if you are catalysis, if you are taking means, so whether it will give the stability or not during the chemical reactions. So catalytic activity will be there or not, that we can check. Stability also we can check based on your material. And biomedical purpose, if you are taking means, so here we will check the drug delivery efficiency, imaging capabilities, and biocompatibility. Everything we will check. If you are taking with the electronics, so there we will check the charge transfer things, and testing the electrical conductivity, the device performance and all we can check. So then if you are taking a food industry, so nano composites, nano biosensors are there. So these are nowadays, these are improving a barrier property for the food packing and all. So extending their shell life. So previously it will be sustained for a few days only. Now whatever the nano composites we are using, so in that it will extend its shelf life, that is there in a nano composites if you are using in a food packing system. Then food safety also. So this here, the spoilage will not be there, then contamination will not be there, pathogen detection, everything we can do, and we can maintain the indicators also will be there in the food products where any spoilage is there, it will indicate that. So that is also there with the nano biosensors. And aerospace and defense, if you are taking means, so lightweight materials, that means nano composites we are using in an aerospace for the lighter and stronger materials, where it will improve the fuel efficiency in the flights and all. So then in the steel, the technology if you are taking means, it will be used as an coating and materials to reduce the radar and infrared rays signatures and all. For that we are using this nano materials, which is making us an one of the coating material for the things, product, whatever we are preparing. And the next one, so this is the case study, silver nanoparticles and antimicrobial coating. So here they have selected the, this is first application is on silver nanoparticles, which is used as an antibacterial coating. And the second one is on, it is a different application. So application of gold nanoparticles for the breast cancer cell detection. So here in the image slide, we can see that A1, A2, A3, A4, A5, A6. So this is the cytotoxicity effect they have shown here. So here initially what they have done means, so here they have collected the gold nanoparticles from a plant material. First of all, they have isolated that one from the plant material. So from that, what they have used means, so this is an trastuzumab. This is an drug where it is an anti-cancer drug. So with this drug, they have combined our gold nanoparticles. So initially, without combining this gold nanoparticles to the drug, whatever we have mentioned in the slide, so there it didn't show the cytotoxicity, it didn't affect the targeted cells in the targeted cells. So but here we are mentioning A1 and A2. If you see that, so there here there is a dark spots in the A2 and all. So there you can show that, there you can find the dark field image in A2. So which showing that there is no signal of the gold nanoparticle. So that means initially it is only with the that drug only, whatever the drug we have selected. Then when a gold nanoparticles were directly conjugated with the drug anti-cancer drug, that is trastuzumab. So here in this, it will bound to the cancer cells. So that means it clearly indicating in the A4 image. If you see, that means, so there is a light scattering. So light scattered here, there you can see the gold nanoparticles, which is affecting that cancer cells. Then after that, in the next slide, next images, we can see that, so by combining these gold nanoparticles, so amino gold nanoparticles, so where it is binded with conjugatedly covalently, it is binded with the anti-cancer drug. Then here it will shows that, so the gold nanoparticles also concentrated on the cancer cells. So slight lower intensity will be there. So if you are seeing this A6 image, so this image will be, but here we can observe that slighter lower intensity in the dark field when compared to the A4. So A2, A4, A6, if you are comparing means in the first A2 slide, we can see that there is no dark field, even though in a dark field also we cannot finding the signals are not there. In A4 side, when you are scattering the light one, when you are mixing your drug with the gold nanoparticles, we can see that scattering of the gold nanoparticles. That means it is affecting on the targeted cancer cells. In A6, you can see that slightly lower intensity of their lower intensity is there. So which is point out that, so when you are mixing, when you are combining your gold nanoparticles directly with the anti-cancer drug, it is showing, even though if you are stored in a freezer only about 2 weeks, so it is lost their activity. So next, while the gold nanoparticles covalently conjugated with this one, where we are showing the stable is there with the storage for about 2 months also. So here the main point what I want to say you is, so when we are injecting, when we are combining with the gold nanoparticles with an anti-cancer drug. So before injecting this gold nanoparticles, the stability of that product of that compound is survival rate will be 2 weeks only. So 1 second. The survival rate in the previous slide, the survival rate of the is very less. Then when you are mixing with the gold nanoparticles with the anti-cancer drug, it is showing the storage and stability will be, we can store it for that 2 months also. That is the thing we want to explain in the previous slide. So the next one is an next slide. So this is an plant material, Morinda citrifolia. So this generally we will call it as a noni fruit, and this noni fruit is having an anti-cancer properties there. So this is which I have done the work. So here generally we have collected this plant material. Here we have selected the fruit of that one. So from the fruit pulp we are used, and we have extracted the fruit pulp from the plant. So then we have studied the studies and all what and all we have mentioned here. So here I have opted a method technique called HPLC technique I have opted. So in the HPLC technique, so what we have done means, so initially we have method development will be done in this plant material, whatever we have selected, that is a noni fruit, so which is having an molecular weight 456.71 grams is there. It is a white crystalline powder. The solubility, that means solvent and all. So here it is soluble in chloroform, alcohol and water. And the category if you are taking means anti-cancer agent. So here this is a plant material. So here the same thing I have done. So isolation, I have selected the plant, I have studied the literature survey. So then I have confirmed that this is the anti-cancer agent is the property. Now I have started the method development in this. So for this method development, I have opted a method called that is an this one HPLC method I have taken. So next slide we'll move on to the HPLC method technique we will follow here. So the next slide we have done with the method development. So method development, before going the method development, we will have the optimized chromatographic conditions will be there. So that means mode of selection. So in which way we are going to separate. So in that way I have selected the HPLC method. Then selection of the solvent, then selection of mobile phase will be done. So after this one we have done the optimized conditions. So in this optimized conditions, so next slide. So this is the optimized conditions. Here we are going to check our plant extract. So after the isolation, after the synthesis, we have taken the plant that means plant material, that fruit pulp. So that we have done with the HPLC method. So these are the parameters. Here we have checked the mobile phase, diluent as there, the flow rate. So 0.5 ml per minute we have taken. In the column column we have taken 18 C18 column we have taken. So by using an UV visible, so we have done with the blank sample, and we have set the UV visible range around 284 nanometers, and injection volume will be 20 will be there when we are running this the HPLC. So method, here we have got the retention time. So by retention time, where we can know that in this retention time, here we have got the 3.278. The remaining things we can find it is under spike compounds. So this we have in the later slides, in the later research purpose, we have removed all the spike by using a column chromatography techniques and all we have done. So there we have removed the spike components, and impurities are also were seen. So that impurities and all we have rectified in our in the later our research. So then we'll move on to the next one. So after developing this is the optimized method. Then after developing the method, we have focused on the validation parameters. So in this validation parameters, we have the specificity, linearity, precision is there, and limit of detection, and system suitability. So these are the various parameters. Once you have developed your method, then we are going with that. So in a specificity, we can find out, we will compare the blank as well as the sample we have compared. So we will find the similar identical retention time only, and there is no interferences during the placebo as well as the sample. So this method we have after confirming the specificity. So we have confirmed that this method is unspecific. That means the blank and all, whatever we have done in the previous optimized conditions, that we have removed the spike and all. So then we got the same retention time is there. So when you are doing with the blank as well as when you are doing with the sample one also. Then we have gone through after this specificity, we have confirmed this method is a specific. So then we have done with the linearity. So where we can draw the next slide, where we can draw the calibration curve between. So next slide, sir. So linearity study was performed by the concentration range. We will change here. So it may varies from 2 to 10 micrograms per ml. So where we have plotted our calibration curve along the concentration versus the peak area, which we have got it from the data. So which shows that, so here it will show some linear curve will be there and the retentions will be 0.99. So which will be within the range only. After this linearity, we can say that the linearity curve of the ursolic acid. So this ursolic acid is one of the main active constituents in that noni fruit. So this is one of the active constant which is we can use it for the anti-cancer thing. So here the retention value we got 0.99. So which is within the limit. That means 2 micrograms. 2 range will be there. So within that range only we got the retention value also. Then we'll move on to the next one, that is a precision. Next slide is precision. Accuracy. So here accuracy also we will take the placebo content. So levels we will change 50, 100. We will change the concentrations. So along with the changing the concentration, we will check the recovery also. How much recovery we can get. So during the process, once our process is done, so how much by changing the concentration, how much placebo we will get. So here we got 98.0 to 102%. So and this is the range generally, but we got 99.3 to 100%. We got the placebo recovery is there after the after done the process and all, after the synthesizing everything, after developing the method and all, we got this much of compound recovery we can get it by using this accuracy method and all. So next one is an precision we can take. So our system suitability. So system suitability means here we are checking the system suitability, how much suitability will be there when you are injecting the sample. So these injections we will do in an intraday and interday also. So when you are doing this, we will check the retention time and peak of area, USP tiling and plate count also we will check. So while we are doing this inter and intra injections, we have found that so sun range will be 0.2% and USP tiling will be at 1.9. So both were within the limit only. Then the next slide, sir. Next slide. And this is the cytotoxicity after the metal, after the detection, after the validating all the parameters. So then we have done with the cytotoxicity effect. So cytotoxicity effect, for this cytotoxicity effect, we have selected the 2 cell lines. So what is an MCF7 cell lines and A549 cell lines. So in this, one lung cancer cell is there and one more is an breast cancer cell lines are there. So we have taken the 2 cancer cell lines. So in that cancer cell lines, we have done the cytotoxicity test along with the concentration. So where we got the values like so 138.67 and 117.67. As you keep on increasing your concentration of your cell lines, then the cytotoxicity, if you are increasing, means the cytotoxicity will be reduced. So that only we have identified. So here this is the slide, only one particular material we have selected, but generally in my research studies I have done the comparative studies. So I have collected another 2 plants also, with that I have compared the studies. So in out of those 3, so this ursolic acid is showing an very less cytotoxicity. If you are increasing the concentration, the cytotoxicity will be less only. The next one. So this is also the parameter where we can do the limit of detection and the precision also. I have told you in the previous slide only, inter and intra injection. So in that, precision is an intermediate injections. So where we are doing our for the ursolic acid, where we can calculate the how much precision is happening during the process. If you are taking the injections, how it is working on it. So that is also which is less than the 2% only it is there. And the next one is on slide. Next one. So these are the images when you are showing the controlling of your urusolic acid after injecting with the cell lines. So then the control A2G will shows the lower concentration and H2O will shows the higher concentration. So this is the higher concentration. When it is in a lower concentration, the images is not applicable. So we'll not see that clearly. If the concentration is increasing, you can see the how your cancer cells are related. So based on this concentrations only, if you are increasing or decreasing the concentration, the cytotoxicity effect will be known to us. So based on these images only, we have plotted that graphs also. And the next one, next slide, sir. And this is the thing we are next we'll focus on to the future scope. So based on this isolation of plant materials, we have many advantages like efficiency and effectiveness are also is there. So and that's sustainability, biocompatibility, cost effectiveness, diverse application, scalability, reduces the toxicity, all these are there. So in sustainability means plant-based synthesis of nanomaterials offers. So overall the conclusion if you are taking means, so the isolation of plant materials. So move on to the next slide only. Next slide. So conclusion we will state that. So after this, after finding all these things, after the extraction, isolation, then characterization, after that we have developed a method. So based on all these things, we have concluded that the isolation of plant materials for the synthesis of nanomaterials will represent a significant advancement in the field of nanotechnology, where it offers a suitable, eco-friendly alternative with the traditional chemical synthesis method and all. And this approach, whatever we are doing, the main thing is it is an biocompatible, cost effectiveness is there, and it is an environmentally safe one. So we can use it for a wide range of applications, not only with the limited things, we can use it for the wide range of applications in all the streams, not only in the medical, not only in the electronics, every field we can use this thing by using the plant-based materials. As a research progress, if you take means scalability and functionalization potentials of the plant-based synthesis will expand more, and the pivotal techniques also we can use for the development of innovative nanomaterials in the various industries. And whatever the information I have shared you that I have selected with these two references, they have I have mentioned in this. So one is on biosynthesis of nanoparticles using the plant extraction and essential oils. And thank you so much. Sarojini ma'am.
Yes, ma'am.
Yes, ma'am. I am done with the presentation. Thank you so much. And this is the acknowledgement thing. I thank our management on behalf of our MBJ College. I thank my principal sir and the head of the department and faculty members who have supported me. And special thanks to Dinesh sir for giving me this opportunity.